Good afternoon, students. Lecture 8 of Modeling and Simulation of Physical Systems, in which we shall cover more examples of Lagrange's method for modeling the physical systems. Our first example is inverted pendulum. It contains a pendulum bar supported on mass m1. The goal of this problem is to sustain a perfectly vertical or nearly vertical orientation of the pendulum bar in order to prevent it from falling on the ground. The mass m1 experiences linear displacement x, and the pose and the position of the pendulum bar is specified by the angular displacement theta. Ideally, we would like to adjust x in order to get theta that is as close to 90 degrees as possible. But for that, we need to find out the relationship between theta and x using a differential equation. In the model of this system, we shall assume that there is some friction being experienced by mass m1. This friction is modeled by the translational damper whose damping coefficient is small b. There is another friction, friction 2, between the pendulum bar and the center point of the mass m1. And this pivot is the one about which the pendulum bar shall rotate. So the friction 2 will be modeled using rotational damper with the damping coefficient capital B. Also note that the mass of the bar is taken as m2 and its center of gravity is shown here somewhere in the middle of the bar. In this problem, we shall not ignore the weight of the mass m2. The weight of the pendulum bar is duly taken into consideration because our whole effort is to prevent the pendulum bar from falling. Therefore, the influence of gravity is fully taken into consideration in the model of the system. Thus, the weight of m2 is non-negligible and the acceleration due to gravity is g, so that the weight of the pendulum bar is going to become the part of the model. Once the appropriate displacement variables have been defined, which in this case are the linear displacement x of mass m1 and the angular displacement theta of the pendulum bar. The next problem, or the next step, is to define the appropriate reference axis of the axis system. We can just say that the x-axis is taken in the horizontal direction and the z-axis is taken in the vertical direction and the y-axis is taken out of the plane as shown here. For the complete description of the model, the translational damper has been included as shown here, and the rotational damper is connected between the center point of mass m1, which also refers to its center of gravity, and some point over here, which is fixed. So one end of the rotational damper is fixed, the other end is connected to the pivot, which is the center of gravity of m1, and it is a pivot about which the pendulum bar shall rotate with an angle theta. Therefore, in order to apply Lagrange's method, we need to calculate the corresponding energy functions. Let us start with the simpler energy function first, the dissipation energy. In this case, there are two components contributing to the dissipation energy, one of them being the dissipation energy due to the translational damper, half b x dot square, then the rotational damper dissipation energy is half capital B theta dot square. That completely defines the dissipation energy function capital R. We next define the potential energy of the system. In this case, it is easy to note that mass M1 has no potential energy. It is located on the x-axis, that is the center of gravity of M1 is on the x-axis, meaning that it doesn't have any height, so the potential energy of M1 is 0. However, there is non-zero, or there can be non-zero potential energy associated with the pendulum bar. So let us calculate the potential energy of the pendulum bar considering its height h. The height of the pendulum bar can vary along its length. Therefore, the way to compute its potential energy is to shrink this pendulum bar to one point, considering this as a point mass, which we know should be taken as the center of mass or the center of gravity. So the height of the pendulum bar will be calculated considering the length or the distance between the pivot and its center of gravity. That length will be L over 2. But what about the height of this center of gravity, h? That will simply be L over 2 times sine theta dot. So the potential energy will be m2g times L over 2 times sine theta. That is the total potential energy of the system, given that there is no other element contributing to the potential energies. Now let us move to the calculation of kinetic energy of the system. Note that the system kinetic energy should take into consideration the translational motion of mass m1, whose motion is defined along x-axis only by the displacement variable x. So that should be half m1 x dot square. However, the kinetic energy of the pendulum bar is a bit complicated to calculate, and the reason is that the pendulum bar has a general motion because its pivot is not stationary. And we have seen such cases before in our previous lectures. More specifically, in the case of two-link manipulator, the pivot of link 2 was non-stationary, and therefore link 2 in a two-link manipulator had a general motion needed to be described by both the translational kinetic energy, both the translational kinetic energy as well as the rotational kinetic energy. So in this case, we'll have to figure out carefully what is the component of translational kinetic energy and what are the components of rotational kinetic energy. In order to compute the total kinetic energy of the system, we shall first focus on the kinetic energy of the pendulum bar. As mentioned earlier, that the kinetic energy of the pendulum bar contains both the translational and rotational components. If we first calculate the translational component, we require the entire pendulum bar mass to be treated as a point mass, and the best location for such treatment will be the center of its mass or the center of gravity. In some sense, we wish to shrink the entire pendulum bar to a point mass at its center of gravity and associate a displacement variable with reference to the global axis. So if this is the global x-axis, and here we have the z-axis, the global z-axis, and this point is taken as the origin, then as the pendulum bar moves, the center of gravity shifts from one point to another, and we assign a displacement variable dCg. And if we take a derivative of the displacement variable, this will give us the velocity, which can be directly used to compute the kinetic energy. However, as has been the case before, in order to simplify the expression and the subsequent manipulation of the expression, we often split the displacement variable into its x component and the y component. So xCg defines the x component of the displacement variable, which is along x-axis, and yCg defines the vertical component of the displacement along y-axis. Essentially, this is not actually yCg. This really represents the vertical displacement. Maybe zCg would have been more appropriate, but anyways, yCg has been used. You could have just used zCg as well. Would have worked just as fine. So once the horizontal and the vertical components of the displacement, the position variables have been computed, then we can just write down the expression for the translational kinetic energy of the pendulum bar. That is half times m2 xCg dot square plus half times m2 yCg dot square. And xCg dot expression shown here, yCg dot expression shown here, and the corresponding squares, square these terms, can be found here as well. So with that, we can finally write down the expression for the translational kinetic energy of the pendulum bar, which is the sum of the kinetic energy in the x-axis and the kinetic energy in the z-axis, which is half times m2 yCg dot square. The expression amounts to half m2 x dot square minus m2 L divided by 2 times x dot theta dot sine theta plus L square over 8 theta dot square. Next, we add another component of the translational kinetic energy, this time due to the translational motion of mass m1. So the new term has been added to the existing expression for the kinetic energy. This new term is half times m1 x dot square. Once the expression for total translational kinetic energy of the system is obtained, we next proceed to the total rotational kinetic energy of the system. In this case, the only element exhibiting rotational motion is the pendulum bar, whose rotational kinetic energy is taken as half times jCg times theta dot square. Now note that jCg is the mass moment of inertia of the pendulum bar as it rotates about its center of gravity, not about the pivot. And this is something we need to pay attention to. Now remember, if a mechanical system contains some mass or inertia element exhibiting a general motion or an arbitrary motion, this can be split into a translational motion and a rotational motion, and we have emphasized this a lot of times before. So in this case, let us consider the pendulum bar of some mass m. In our example, this is actually m2, and it has some mass moment of inertia about its center of gravity that is represented as jCg. The center of gravity has been shown here by these points. Assuming that the pendulum bar like strip shown here has some general motion or arbitrary motion, it moves from its initial position over here to the final position over here, it is same as the bar first experiences a translational motion. So essentially this one over here is taken as the initial position, the right hand side. So there is a translational motion, therefore there's a linear displacement specified by some linear displacement variable such as x, and that shifts the bar from one position, or the center of gravity from one position to the final position over here. Remember, in the translational motion, there is no change in the orientation of the bar. So you can just imagine that the initial position and the final position, they are joined with the help of a straight line segment as shown here. And the two poses of the pendulum bar as shown here, they are aligned, or they are parallel. So the pose or the orientation has not been changed. Then the arbitrary motion, the other component of it, is the rotational motion. So remember, we are decomposing the arbitrary motion into the translational motion and the rotational motion. So how can we describe the rotational motion? Well, so once over here the pendulum bar has relocated to a new position, I mean its center of gravity without the change of orientation, then the rotational element will just rotate this bar about its center of gravity. So there is going to be some angular motion. So in this rotational component of the motion, the pendulum bar center of gravity will not be displaced as happened in the case of translational motion. So only the orientation or the rotation or the pose is going to change, and that comprises the rotational element. And this rotation occurs about its center of gravity. So in summary, we are saying that if the initial pose of the pendulum bar is this one and the final pose is this, then this can be, so how can we get the final pose from the initial pose? Well, we just move the pendulum bar along this displacement, along the direction of this displacement variable x as shown here, without change in the orientation. And once the center of gravity has reached its new position, all we need to do to obtain the final pose is to rotate the bar about its center of gravity. So the kinetic energy due to the translational motion is simply half times x dot square times the mass, but the rotational component of the arbitrary motion will be half times theta dot square, that's because the angular rotation, times the mass moment of inertia of the object, which is the pendulum bar, about its center of gravity. So this is very important. So remember, we are decomposing arbitrary motion into translational motion, which simply displaces the center of gravity without change in the orientation of the object. And the next step in which we describe the rotational motion, the center of gravity is not displaced, only the orientation changes. And when that happens, we need to consider the mass moment of inertia about the center of gravity. So half jcg times theta dot square. So even though in our problem the pendulum bar is actually rotating about the pivot which does not coincide with its center of gravity, we can still decompose its motion into translational motion and the rotational motion, in which the rotation occurs about the center of gravity. Therefore, the mass moment of inertia in the rotational component of the kinetic energy should be taken about the center of gravity. And the same applies to the two link manipulator problem, where the mass moment of inertia of link 2 should be taken as the mass moment of inertia about the center of gravity of link 2. Alright, so I would like to conclude my long speech with the final steps of the problem. The total kinetic energy expression would then contain the sum of the rotational kinetic energy and the translational kinetic energy of the system. That defines the overall kinetic energy function T. Then, in order to develop the differential equation describing the relationship between the displacement variable theta and x, we need to take the partial derivative of the kinetic energy with respect to the displacement variable to be used in the Lagrange equation. So our first displacement variable shall be theta and the second one will be x. So we compute the partial derivative of kinetic energy with respect to theta dot, the angular velocity, and obtain this expression. And taking the time derivative of this expression gives us d over dt applied to partial t with respect to partial theta dot, this expression. We also calculate the partial derivative of kinetic energy with respect to the x dot, that is the linear velocity associated with mass m1, and taking the time derivative afterwards yields this expression. If we take a partial derivative of kinetic energy with respect to x, we should get 0. That's because kinetic energy does not depend on the displacement. It only depends on the velocity. So that's the velocity of mass m1. That gives us 0. However, if we take a partial derivative of kinetic energy with respect to theta, the angular displacement, that is not necessarily 0. In fact, we get this expression that contains cosine theta multiplied by x dot theta dot m2l divided by 2 with minus sign. Alongside the partial derivative of the dissipation energy with reference to x dot gives bx dot, small b, and the partial derivative of dissipation energy with respect to theta dot equals capital B times theta dot. So in the last step, maybe this really should have been before the last step, but anyways, we have actually defined the position variables to be the displacement variable for mass m1, that is x, and the angular displacement variable describing the angular motion of the pendulum bar, that's theta. And because there is no loading function associated with either displacement variable, so we're going to set their corresponding loadings to be equal to 0. Hence, the right hand side of the Lagrange equation, there are going to be two of them, one based upon the derivatives of energy with respect to the velocity and the displacement of m1. The other Lagrange equation will be based upon the derivative of angular velocity, that is of the pendulum bar, or its angular displacement theta. On the right hand side of both equations is 0. The left hand side, the components of the left hand sides have been pre-computed. You can just plug those in and obtain the final expression obtained from the Lagrange equation of motion. Remember, there is a potential energy term involved in the system associated with the potential energy of the pendulum bar. So this term is basically partial u taken with respect to partial theta. That must be included. As a homework exercise, you will be required to solve a variant of a inverted pendulum, which is actually a more familiar version of the inverted pendulum problem, in which we assume that the mass of the pendulum rod is negligible or negligibly small, so that can be essentially taken as 0. But at the tip of the pendulum bar, we have a mass m2, and the problem of the inverted pendulum in this case is that we like to make this angle theta as small as possible. This time this angle theta is taken with respect to this vertical z-axis, or you can just take it as y-axis, whatever it seems more convenient, by applying appropriate displacement to the mass m1. who is experiencing some external force instead of friction. In this case, there is no friction, but there is some external force which is perhaps responsible for its displacement along the x-axis. So you will write the equations of motion for the modified and perhaps more familiar inverted pendulum problem, and the other part of the problem is to answer the question that is it possible to develop the state space representation of the system. If it is possible, then you will develop the state space representation. If not, then explain why is it not possible. And the last problem is the planetary gear system, which finds lots of application in the motor drive units used in so many applications in mechatronic system. In the planetary gear system, there is an inner ring that's called the sun gear that meshes with the outer gear that's called this ring gear. And the sun gear meshes with the ring gear indirectly with the help of a set of smaller gears that's called the planet gears. So sun and ring gear rotate about the stationary point O. So they are concentric. So the stationary point O on the z-axis, that is axis that is perpendicular to the xy plane. However, the planetary gear behave differently. In some sense, the planetary gear motion will be in the space between the sun gear and the ring gear, and they are rotating about their moving axis. It is very similar to the case of rolling wheel without slip in our lecture 5 and 7. So the same assumptions will be applied here. We can just say that the sun gear meshes with a planet gear, which in turn meshes with the ring gear. Therefore, as the sun gear rotates, it rotates the planet gears, which in turn rotates the ring gear. And the same can be understood if the torque, conversely, we can say that if we apply some rotation to the ring gear, that rotation can be imparted to the sun gear with the help of planet gear. So it can go both ways, but the role of the planet gear is very important. They are going to roll in the space between the sun gear and the planet gear. A more intuitive snapshot that we have actually explained already is that the sun gear, suppose that rotates in the counterclockwise direction at an angle θ1, it is meshing with the planet gear, essentially causing it to rotate in the opposite direction, that's θ2. And when the planet gear meshes with the sun gear, it will rotate the sun gear again in the opposite direction to θ2, that's θ3. That actually the direction is actually the opposite, so it will be in this direction. So the meshing principle states that the radius of the sun gear, if it is taken as r1, when multiplied with θ1, gives us the total linear displacement at the point where the sun gear comes in contact with the planet gear. It is same as r2 times θ2, where r2 is the radius of the planet gear. It is same as r3 times θ3, where r3 is the radius of the ring gear. So there's a typo here, that really is the ring. So the linear displacement at the point of contact between the two gears is the same, and we have this relationship. r1 θ1 equals to r2 θ2 equals to r3 θ3. In this problem, we shall write the equation of motion for one of the planet gears, planet gear A, whose radius is small r, and in comparison, the radius of the sun gear is capital R minus small r. The initial pose of the planet gear A is such that OZ is perfectly vertical, and a segment of this vertical line, that is AB, as shown here, is also perfectly vertical. However, as the planet gear A rolls around the periphery of the Sun gear, it moves in an arc and relocates its center to new point Z prime. And once it reaches its final pose, then the initially vertical line AB has now become a slanted line A prime B prime. And A prime B prime makes an angle theta with respect to a vertical axis of the system that is like the global y-axis of the system. So call this global y-axis. We are actually interested in relating the length of this arc with the angular displacement variables such as theta and beta. So in some sense, beta describes the angular displacement of the Sun gear, and theta describes the angular displacement of the planet gear. What is the relationship between theta and beta? We need this relationship to write the equation of motion. However, note that the relationship between theta and beta is somewhat different in the textbook, in which they involve another displacement variable, that is gamma, which is the angle between the line A prime B prime and the line that radially connects the center of the Sun gear and the center of the planet gear. However, in our solution, we shall not be using gamma at all. We shall first relate theta with beta, utilizing the information of the arc length along which the planet gear has moved. So we define and explicitly write the global axis of the system, so x-axis and y-axis. In order to understand the length of the arc along which the planet gear A was moving, we first note that the planet gear A in its initial pose has a vertical line describing its initial position or initial pose AB with the center at Z. It moves from Z to Z prime. And in this process, because the planet gear A has been rolling around the periphery of the Sun gear, as it rolls, the vertical line becomes slanted A prime B prime, making an angle theta with reference to the global y-axis. What is the distance between Z and Z prime? Well, that is just r times theta, where r is the radius of the planet gear and theta is the angle made by the y-axis. This expression is true because the center has been displaced perfectly along the x-axis. So we say that the gear A, planet gear A, rolls on a horizontal line displacing its center by distance z, Z prime. However, we know that the final position of the center of the planet gear A does not lie on the x-axis, rather it was shifted upward because the motion path is actually an arc. Therefore, to understand this situation, we can just say that if this was the previous position of the center of the planet gear A, so this was previous Z prime, so we have just shifted the entire planet gear A without rotation to its new position over here. So from this point to to over here, the planet gear A has not rolled at all. It has not rotated at all. So that the angular relationship between A prime, B prime and the global y-axis remains preserved. And when we move the center from its previous position to this new position, one of the things that should also be preserved is that the arc length z and z prime, this new z prime, should be the same as before. That is r theta. So in this step, we say that the planet gear A does not roll, but simply relocated northwest, preserving the arc length that connects the center, initial central position of the planet gear A to the final center position of the planet gear A. Therefore, we can just say that the arc length has been preserved. Z prime is still r theta. Therefore, this distance is small r times theta. The arc length has been computed. But we don't have related theta. We haven't yet related theta with beta. Now we introduce the other way to calculate this arc length, that is realizing that this distance OZ is the same as OZ prime, because Z and Z prime are connected by an arc as part of the circle. So the important thing from the kinematic analysis of this problem is that as the planet gear A rolls around the sun gear, its path is part of a segment of a circle, that is the arc. Hence OZ and OZ prime represents the same distance. So this arc length can also be written as the radius times the angle beta. So beta times r is the same as r theta. So this gives us a relationship between beta and theta, that is theta is equal to capital R over small r times beta. In summary, we say that with respect to the global y-axis, the planet gear A rotates by an angle theta. Although with respect to its local y-axis, where is local y-axis? Well, local y-axis is that which is changing with its position as it moves from an initial position to the final position, that is this line over here. So remember, the initial local y-axis coincides, it was actually parallel or the same as the global y-axis, but the final local y-axis, so-called local y-axis of planet gear A, has now been changed. The angular displacement between A prime B prime line with the local y-axis is AB. However, as I said earlier, that we are not going to take gamma into our calculation. We have simply directly related theta with beta as discussed in this slide. All right, so once kinematic analysis is complete, we can and we have noted that theta and beta are related by the following equation. The formal problem statement requires us to relate theta with the force. There is some force that is being applied to the center of the planet gear A, that is at point X, Z. That force needs to be related with the angular displacement theta of the planet gear A. And remember, theta is the angular displacement of the planet gear A with reference to the global y-axis, which is this perfectly vertical line. To write down these equations, we shall use the mass moment of inertia as it rotates about its center of gravity. So that term, as we've seen, is often required in writing equations of motion, that is JCG. And F is the force applied to the center of gravity of the planet gear, A in this case. We are going to use Lagrange method to write equation of motion, and we need to first define the displacement variable as well as the corresponding loading function. In this case, the force is applied to the center of planet gear, that is at point C, and therefore the loading function is simply the force. The corresponding displacement variable is the displacement at point C, which we know is described by the linear displacement, that is capital R times beta, the arc length. We know that there is only one component of energy in this problem, that is the kinetic energy of the planet gear A. Again, a gentle reminder that we are not required to write the equation of motion of the sun or the ring gear, so their kinetic energies are ignored. And there are no elements contributing to the dissipation or the potential energy. Specifically, there is no potential energy in the system because the gear system is placed in the XY axis. To find the expression of kinetic energy, as has been the case before, we first need to define an appropriate axis system with respect to which we shall define the position of the planet gear A. So as shown here in the diagram, there is a triangle O, Z, and Z prime. Z represents the center point of the planet gear A at its initial position, and Z prime represents the center point of the planet gear A in its final position, and O represents the center of the sun gear. To specify the position variable, we can just take the reference axis system as shown here, x-axis, y-axis, and the origin coincides with the center of the planet gear A at its initial position. The triangle OZO prime is actually a union of two right angle triangles, OPZ prime, which is this triangle, and PZZ prime, which is this triangle. Now we need to define the position of the planet gear A more specifically, because this is the final position of the planet gear A, and it has been displaced from its initial position, which is the origin of our axis system. What are the x and the y components of the position variable? Call them xz prime and yz prime. Then simple trigonometry shows that xz prime is nothing but r times sine beta, and yz prime is the same as pz distance, the same as oz minus op, that is r times 1 minus cosine beta. Computing the time derivative of both the x and the y components of the displacement variable will give us the following expression. With the help of which we can write the expression of the translational kinetic energy of the planet gear A. That is becomes half time m times xz prime dot whole square plus half times m times yz prime dot whole square, to get half time m times r square, capital R square times beta dot square. Next, we write the expression for the total rotational kinetic energy. And here we need to be a bit careful to write the expression of rotational kinetic energy, as we know that the planet gear A makes, when rotates from its initial position to the final position, makes an angle theta with respect to the global y-axis. So remember, whenever we wish to write down the expression of kinetic of the energy function, the corresponding displacement variables must be carefully selected, and that must be done with reference to the global axis system. The total kinetic energy will then be half times jcg theta dot square plus m capital R square beta dot square. Once expression of total kinetic energy is obtained, we need to make some substitution before we calculate the partial derivative. So remember that our displacement variable is q1, that is the arc length z prime, that is capital R times beta. We actually need to calculate the partial derivative of kinetic energy with respect to our displacement variable, that is q1 and its dot. So partial t over partial q1 dot. That can be computed with the help of a chain rule, because partial t is currently written as a function of beta and theta. And we know that theta and theta dot can be represented in the form of beta dot, beta and beta dot respectively. So remember, we need to calculate the partial derivative of kinetic energy with respect to the displacement variable to be used in the Lagrange equation, that is q1. Another important substitution is the fact that beta equals to small r over capital R times theta. Therefore, if we take a derivative on both sides, we get beta dot equals to small r over capital R times theta dot, and we can just say d theta dot divided by d beta dot, that is capital R over small r. So substituting these into the partial derivative of kinetic energy with respect to partial beta dot gives us this expression, and here we substitute the expression of beta dot, that is small r over capital R, and we get the whole expression in the form of theta dot only, which is this. Our goal is to calculate the partial derivative of kinetic energy with respect to q1 dot. So we apply chain rule, and this requires us to divide the whole expression previously obtained with 1 over capital R. The final expression of partial derivative of kinetic energy with respect to q1 dot is this. And taking the time derivative of the partial derivative of kinetic energy with respect to q1 dot simply converts theta dot into theta double dot. What about partial derivative of kinetic energy with respect to q1, that is just displacement? Well, that should be 0, because kinetic energy does not depend on displacement. It is only a function of velocity. The dissipation energy function as well as the potential energy function are both 0, hence their corresponding partial derivatives. The final Lagrange equation with the calculation of above quantities, partial derivatives, sets the right hand side to the loading function force equals to jcg divided by small r plus mr, the whole of this sum multiplied by theta double dot. It's the same expression as equation 3.136 given in the textbook. We obtain this expression from a different route, that is by using Lagrange's method. The end result, however, remains unchanged. As part of your homework exercise, you are required to solve following examples and problems. The first of them being example 3.14. The example 3.14 is the hoisting system. There is another example 3.16 that is probably the first example in the textbook where the Lagrange method has been applied. And then you should also try to solve the end chapter problem 3.31 parts A, B, and C. Alright, so this is the end of our lecture 8. I hope you enjoyed this lecture, and we shall have a follow-up Q&A session on Thursday at 2 p.m. Till then, stay safe and have a nice day. Bye-bye.